This lesson deals with lab number 8, design of a room equalizer. If you're listening to music in a confined space, the furniture, the drapes, the walls, and other objects in a room can cause amplitude and phase distortion in the audio band. A room equalizer attempts to correct this by dividing the audio band up into smaller bands of frequencies where the signals can be amplified, attenuated, or just left alone. We refer to this as boosting, cutting, or just flat response. In this lab, we're going to ask you to design a system. One way to do that is to draw what's called a block diagram. This is a pictorial model of a system where we use boxes to describe the behavior of the circuit, and then we design the pieces to go in the boxes. Now you'll need to bring to lab an MP3 or a digital audio player as a source of sound, and we have a right and left channel. Now if we design circuitry to go with this, we're going to have to design one for the right and one for the left. Now to make this a little bit easier, I'm going to have you add the right and left channel together and create what's called a monaural system. This will cut the work in half. Now if you want to build the full stereo system, you can, but you'll need to double the number of parts that are in the parts list. So we take one source of sound, and now I want to be able to take certain bands of frequencies and make them louder or softer, do the correction for the objects that are in my room. I use 3 bandpass filters. It's a low value of F0 in the audio band, something in the middle, and something at the high end. So what I've got coming out of here now is my music broken down into 3 bands of frequencies, which will contain most of the sound that I have. Now I may want to make this particular output louder or softer. I got my bandpass characteristic, and then I'm going to put it through a circuit where I'm going to be able to give it some gain. I'm going to do that with a potentiometer. So an op amp will give me some gain, and a pot will allow me to adjust the signal that's coming out of here. Be able to boost it, or perhaps maybe cut it, make it smaller by just making the voltage divider just go to 0. We're going to set the center point of it such that the gain is equal to 1, which is going to pass the signal. Do that for 3 different frequencies. I'm going to add those together with a summing circuit with 3 pots, and those pots will allow us to adjust the volume for that band of frequencies. Now the summing circuit is going to put our music back together again with some bands louder, some bands softer, some bands maybe not manipulated at all. And lastly, we'll put it through the power amplifier we designed in our microphone lab, and then drive a speaker with it. So the first part of our design needs a summing amplifier, and we actually did this in ECE 201 in supplemental problem 410. Here I have 2 inputs, 1 output, and we're going to add these 2 results together with a scale factor and a sign change. So let's take the results, and they're shown below. I'll let this be my left channel and my right channel. The output here, we could just derive the results again. If you just do superposition, set this equal to 0, the gain is minus RF over R1 times V1. And set this one equal to 0, and the gain is equal to minus RF over R2 times V2. And of course, V1 is V left and V2 is V right. And this is my monaural output. If I make the resistors all equal to each other, then I just get simply the summation of the 2 inputs with a sign change. Now, what does a sign change mean? Well, it's going to flip the signal over. So effectively, it's like getting a time delay. But since we don't know when the music starts, having a time delay won't be able to be detected. So we'll be able to pass the signal through with just a time delay. Our next block is a bandpass filter, and in Lab 7 we use this structure to create a second order bandpass filter with a transfer function that's shown here. Here we've got our monaural summed inputs as the input to this circuit. The output then would be one of 3 bandpass filters. So here's the transfer function that we derived. We showed that it was a second order bandpass filter. In Lab 7, we also developed a design procedure for this bandpass filter where we picked 2 capacitors equal to each other. So given the values of H0, Q0, and omega naught, and with this constraint, we found that Q0 had to be greater than the square root of H0 over 2. Now if that's not true, we'll have to pick some other constraint here. But I want to pick my design spec so that this will work. Then we showed we could pick the resistor R5, R1, and R2 in terms of these 3 specs and this initial pick. So if these become impractical, then we go back and modify our first pick. And so we use this design procedure to design our 3 center frequencies for our 3 bandpass filters. Our next task is to specify the 3 center frequencies of our bandpass filters to broadly cover the audio band from 20 Hz to 20 kHz. Now what do commercial equalizers do? Well, they actually do an octave spacing starting at 16 Hz, and it takes about 10 bandpass filters to cover the audio band. This is great coverage, but that's a lot of circuits to build, so let's do something a little bit simpler, but use a similar idea. Let's pick F02 to be roughly the logarithmic center of the audio band, and then let's go back 2 octaves for F01, and let's go forward 2 octaves for F03. That'll give us a pretty good coverage if we have a wide bandpass filter. Now the value of F02, I vary each semester so the design is different every semester, and that keeps everybody honest so we can pass down results from one semester to another. And now we got the values of F01, F02, and F03 for our 3 bandpass filters. What about H0? Okay, let's look at a commercial equalizer. They typically have gains for boosting of 12 dB and cutting for minus 12 dB. What does that correspond to? Well, 12 dB, if you divide that by 20 and make it the power of 10 is equal to 4, and do the same thing for minus 12 dB, you get 1/4. Bandpass filter has its biggest gain at F0, and that's the value of H0, so let's let that equal 4. The 1/4 we'll get from the potentiometers in our summing circuit, and we'll take a look at that in a little bit. Our next task is to pick the value of Q0. From our design procedure, Q0 needs to be greater than H0 over 2, and we now know that our design H0 is 4, so Q0 needs to be greater than 1.414. Now, as I said in ECE 202, Q0 is a measure of sharpness of a bandpass filter. So we don't want to pick this too large, otherwise we'll have really just a small band of frequencies instead of a wide band of frequencies between 20 Hz and 20 kHz. Now here too, again, I vary the value of Q0 each semester so we get a different result from semester to semester. So you can find the value of the F0s and the Q0 in the lab itself. Our next block is a variable summer. So let's take our summing circuit and we'll add a third one here from what we did on page 2. And now let's add a pot coming out of each of our bandpass filters. And when I put this pot all the way to the top, let's make the signal get louder. And when I put it all the way to the bottom, I'm going to get 0, so I'll get nothing out. And let's make the middle maybe a gain of 1. We'll solve for those numbers in a few more pages. Do the same thing for VIII. This is our second bandpass filter in the logarithmic center of the audio band. And this is going to be at 2 octaves higher. And of course, this one is 2 octaves lower from the center frequency F02. Let's summarize where we are in our design. So our audio signal, which we'll call our mono input, is fed into 3 bandpass filters, each of which passes a band of frequencies around some F0 sub I. The variable summer then takes the output of these 3 filters and reassembles the audio band from 20 Hz to 20 kHz. With the pot, we can take each of these smaller band of frequencies and make them louder, softer, or just leave them alone. And that's where our design is so far. Let's take a look at our next tasks. This is in words what I just said on the previous page. Now next, we need to pick the values for the resistors. If we want the center position of the pot to give a gain of 1, then we could use this to pick the value of the feedback resistor if we select the values for the pot and the input resistors. If you look at section 3 of the lab, you'll see that there are values given for the pot and the resistors R1, R2, and R3. And again, I vary these each semester to get the results to be different from year to year. Our next task is to pick the feedback resistor in the variable summer. And what we want to do with the variable summer is when a pot is set in the center position to get a gain of 1. Let's set the other 2 pots equal to 0 and just have the output due to the first filter. Now if we're at the center frequency, the output would be H0 times the input, which is our V monaural. Now in the center position, we have half value for each pot, and then looking into the summer, we have a input resistance of R1 for the first connection. The feedback resistor over R1 is equal to our gain, but it's negative, so we'll put the minus sign this way. So this is the output of the equalizer due to one of the inputs. All right, so that's going to equal the minus RF over R1 times V sub X. This is the input voltage to that variable summer. But what's the value here? Well, it's just a voltage divider. So it's going to be these 2 in parallel over these 2 in parallel, voltage divided with R pot over 2 times the input, which is H0 times V monaural. Now we can solve that to find the output due to one of the bandpass filters due to the monaural input. And that's just going to be equal to H0, which is here, times this expression, times minus RF over R1. And we're going to set that equal to 1. What I'd like you to do now is to solve this equation for the value of R sub F, since we know the value of R1, H0, and R pot. Now we can do the same thing again for the other 2 pots, but if we're going to pick the resistors R1, R2, and R3 to be equal to each other, we'll get the same value for R sub F. Our next block in our block diagram is the power amplifier with volume control, but we've already done this in Lab 5, so let's just go grab that circuit. We used a 50K pot, but we're going to use 100K pots for this particular lab with some adjustment knobs put on them, so it's a little easier to adjust the volume and also our equalization. I can calculate the frequency of this high-pass filter. It's 1 over 2 pi R times C, and everything above that it'll pass. So that's going to be a little bit lower in frequency than we had the 50K pot. We analyzed this circuit and we built it, and we found that the gain was equal to 11 times alpha, where alpha is between 0 and 1. So we'll adjust the volume of the output, just like we did in the microphone lab. So before you come to lab, pick the resistors and capacitors that are not specified in these lab lecture notes and in section 3 of Lab 8. Now the components that are available in your parts box are actually labeled on the cover. Use the nearest standard value for your design components, but you can use series or parallel combinations to get close. As we discussed in Lab 7, we want to pick resistors between 1K and 1 megohm. When they're below 1K, we tend to draw too much current, and when they're above 1 megohm, we tend to generate noise. We'll talk more about these things in later courses. Now for active filters, we'll pick capacitors between 200 picofarads and 0.1 microfarad. Below this, we begin to see effects of stray capacitance. In other words, two wires next to each other are a few picofarads, and that can affect our calculated results. If you go above 0.1 microfarad, you tend to get electrolytic capacitors, and they have a very high series resistance. So we want to stay between these two values, and we'll have very few problems with the non-ideal op-amp. Before you come to lab, sketch out your complete design and label all the components on your schematic. And so lastly, the purpose of this lab is to design a room equalizer to compensate for furniture, drapes, walls, or rugs that could cause amplitude and phase distortion. We're dividing the audio band up into a series of smaller bands, and we're going to manipulate those bands, giving some boosting, some cutting, or passing the signals. We've also simplified our design by making a monaural system. But again, if you want to do a stereo system, please go right ahead, but remember you have to order roughly twice the amount of parts that we have in the parts list. The concepts that we covered were designing a stereo to monaural converter, determining design constraints and component selection for the bandpass filters of our equalizer, and lastly we designed the variable summer. And this is lab number 8, room equalizer design.